Good afternoon, and we continue our discussion of probability. This video is going to be a little different. You see your yellow board in front of you. I've also got a PDF here um, that I will post up on the Canvas page as well, so you can take a look at this. And I'm going to be swapping in between these things. And you can see, yeah, we're talking about something called abduction. And I said, no, we're not kidnapping anyone. Uh, we'll get back to that in a second. So we're over here at the moment now, and there are a few introductory remarks that I want to make here before we proceed. The first introductory remark I want to make is I want to talk about a symbol that we use very frequently in mathematics and logic, and it is very simple. It's an arrow, and it points to the right. And this is sometimes referred to as implication. Okay. Some people could say it's if then. Some people might say it means causes. In other words, if I write something like this, for example, if I say A implies B, okay, so notice what I said here. I said A implies B. It also could be read as if A, then B. It could be read as A causes B. These all mean the same thing. And we're going to be using this symbol a lot. Again, I'm going to try and make nice clean arrows there. But I want you to be aware of that. The other thing is I want you to recall this thing that we talked about before, this conditional probability. And we talked about the probability of A given B is equal to the probability of A intersection B over the probability of B. Okay, so you should be okay with that. Now I want you to consider the following situation. And I want to assume you're not feeling well and you go to the doctor. So you go to the doctor, and the doctor says, "What's wrong?" And you say a couple of things. So you say, "I have fever. Sniffly nose, bad cough." And the doctor goes, which is always very important. You have the flu. Okay, now that is not a completely unrealistic exchange to have with your doctor. Some other things might be said. But first of all, I want you to note what's going on here. You have listed a bunch of symptoms. And the symptoms you have listed are fever, sniffly nose, and cough. And what the doctor has done is the doctor has come up with a disease. Okay, and the disease that the doctor came up with was flu. F-L-U. Now, I want you to think about the relationship between the symptoms and the disease. And it appears that what has gone on here is the doctor's thinking has been that the symptoms imply the disease. Okay? But in fact, we know that that's not the case. We know that in fact it really goes the other way, that disease implies symptoms. Okay? That in fact, this is kind of faulty logic here to think that symptoms implies disease. It clearly goes the other way. And notice here I'm using this implication now. Symptoms don't cause the disease. The disease causes the symptoms. Okay? So that brings us to the whole topic of today's discussion, which is this thing called abduction. And just as a side note here, I think it's interesting to consider the following three modes of thinking about things. So we want to talk about deduction, induction, and abduction. And you can read this for yourself. Deduction is finding the effect given the cause and the rule. Induction is finding the rule given the cause and the effect. And abduction is finding the cause given the rule and the effect. So you can see that there are three different quantities that we are dealing with here. Okay, so we are dealing with the effect, we are dealing with the cause, and we're dealing with the rule. Remember, the rule is the thing that goes like this. Okay, over here is the effect. Over here is the cause. So if you think of this, so deduction, you want to find this given this and the whole rule. Okay, now remember, the whole rule, this whole thing right here is the rule. Okay, induction says you're given a bunch of causes and effects and you're trying to find the rule. And abduction is really the strange one. It says you're trying to find the cause given that you have the rule and the effect. Now, it may look a little confusing, but let's look at the next slide here, and I think you can see what's going on. So, for example, if we want to talk about deduction, okay, and I am given all men are mortal, okay. Now this, okay, this right here, this is the rule. Okay? This over here, Socrates is a man, that is the cause. And over here, therefore Socrates is mortal, that is the effect. Okay? Likewise, what we're doing over here in induction is we have done the following. We see a swan, and we note that it's white. And I'll call this swan 1. And then we see swan 2, and we note that it's white. And we see swan 3, and we note that it's white. And from that, we make a rule. Okay? We go, therefore, swans are white. We have seen over here, we are seeing a bunch of causes. Over here, we're seeing a bunch of effects. And what we're doing is we're putting this all together, and we're making a rule. Okay, so here's the rule. Now here is abduction. And what's going on here is we have a rule, drunk people do not walk straight, and we have that Jack is not walking straight, therefore Jack is drunk. In other words, over here is we have the rule, cause implies effect, and we're also given the effect. And what we're doing over here is we're concluding the cause. And the point is that this really is not valid logic. But that doesn't mean that this is not necessarily a valid thing to do. So we can see over here that abduction takes the form of this. It's of if A, then B, and we're given B, and we conclude A. You might recall induction and I apologize for these goofy things showing up on the screen, induction would take more of the form if I have A implies B and I'm given A, I conclude B. So this thing in general, I'm just going to say in general, okay, it's not valid logic. But that doesn't mean that we're not going to have a use for it. So we're going to come back over here now. And now we're going to talk a little bit more about induction. So basically, I want you to remember the following, that diseases cause symptoms. Okay, it's not the case that symptoms cause diseases. So it makes perfectly good sense to talk about what is the probability of a symptom given a disease. In other words, it makes sense to ask about what is the probability of fever given that you have the flu. Again, this is a symptom, this is a disease. But it looks like what the doctor is doing, and this is what the doctor is doing, is we're asking, well, what is the probability of the flu doesn't have an E in it, given that you have a fever? Okay, this is abduction. And we can answer this. That's the thing that's really weird. Okay, we can answer this with certain information. And the question is what is that information? Well, I will discuss that as soon as I save this slide. So what I want you to do, maybe some of you've heard this, it's been in the news a lot lately. Down in Atlanta, there is something called the CDC, and this is a federal agency, and this is the Center for Disease Control. And what these folks do at the CDC is they collect a lot of data. And in fact, what is supposed to happen in the United States is that whenever you go see a doctor and the doctor diagnoses you with some strange disease, okay? And in fact, why don't we for now make it even a little more theoretical? Anytime you have any condition at all and the doctor examines you, the doctor is supposed to call the CDC up and say, okay, I've got somebody that's got the flu. Or, okay, I've got somebody that's got hepatitis A. Or, okay, I've got somebody that's got the measles. Or a whole bunch of other things. So what the CDC is able to do is they just keep track of these things. The CDC has a rough idea of what the population of America is, and they keep track of all of these things over here. So they know that for the flu, maybe there are 3,286,579 cases of this. And maybe for Hep A, there are 2,463,123. And for measles, there's some number here. And you can imagine that the CDC has a list of all of these diseases, and it has a list of how many incidences of these they have. And of course, from that, they can compute a probability. So that maybe the probability now of the flu, it's going to be this divided by the total population. For hepatitis A, it would be this divided by the total population. So maybe this is something like 0.01, and maybe this is 0.008, and maybe over here this is 0.006. So in fact, we can imagine the following, that there are all of these different diseases, and I'll say D1, D2, D3, all the way up to some D sub n, and the CDC can tell you what the probability of DI is for any particular disease. That doesn't seem so unreasonable. Now, there are other things that are going to go on. When you call the CDC, let me move this. So you, or the doctor, you call the CDC, patient has disease D sub J. And the CDC is going to ask you, what symptoms do you see? So you're going to sit there and you're going to say, well, I saw a fever, and I saw a sniffly nose, and I saw a dry cough. And what's going to happen now, remember, the CDC is collecting lots of data. And here is DJ. And remember, DJ is some disease. And now we come over here. And we can start to keep count of fever, sniffly nose, dry cough, and all sorts of other things. And what the CDC can do here is it can keep track of some numbers here. 1, 2, 3, 9, 8, 7. 5, 8, 6, 1, 2, 3. 1,407,000. And what's going on here is it's not only keeping these numbers for DJ, but it's keeping it for all these other ones, for D1, D2, all the way up there. And we've got this whole big table here of these different symptoms, okay, and these different diseases. Now, note what's going on here. We can calculate over here. We could, if we think of this as symptom 1, and this is symptom 2, and this is symptom 3, all the way up to something. If we are, what these numbers correspond to in here, okay, we can actually calculate what is the probability of some symptom of S2, say, given DJ. Okay, if we know the total number of people that have this particular disease, we put that in the denominator, we put this in the numerator, and what we have there is we now have the probability of this symptom given this disease. Now, the one last thing that we can do over here is we can draw a line at the bottom of this table, and at the bottom of this table, we can come up with totals. So over here, this is going to be the total number of fevers I have over all the diseases. And if I come over here, I am going to get the total of a sniffly nose over all of these diseases. And if I come over here, I am going to get the total of all the dry coughs, okay, over all of these diseases. Now again, what I can do is I know my total population that I'm dealing with, so I can look at the ratio of this number over the total population, and that's giving me the probability of just this particular symptom. If I come over here and look at the total for sniffly nose, okay, and I put that in the numerator and I put the population in the denominator, over here I'm going to get the probability of S2. And likewise over here, the probability of S3. And I can do this for all of the symptoms that I'm keeping track of. So let's think about what's going on here now. What do I have, or what does the CDC have? Well, the CDC has the probability of D sub j for every disease, hopefully, D sub j. It also has the probability of S sub I for every symptom, S sub I, and then it also has the probability of S sub I given D sub j, which means given one has D sub j, what is the likelihood they have symptom S sub I? So we have all of this information at our disposal. And now here's the abduction here. What is the probability of a particular disease given S sub I? This is abduction. Okay? Because what we seem to be doing here is saying that the symptom implies the disease. Okay? So we need the rule for figuring out how we can do abduction. And this is going to be some mathematical trickery, and it works. So there's something called Bayes' rule. And let us go back and let us remember that we talked about the probability of A given B is equal to the probability of A intersection B over the probability of B. And there are a couple of things I want you to note. First of all, that the probability of A intersection B is equal to the probability of B intersection A. It's completely symmetric here. And what I want you to note over here, I'm going to multiply both sides by P of B, so I get that P of B times the probability of A given B is equal to the probability of A intersection B, which by what we said over here, that is the same thing as the probability of B intersection A. So Bayes' rule says, well, we know about this. Suppose I want, how do I find, and I'm just going to reverse these two, and you can see what I'm doing. I'm reversing symptom and disease. How do I find the probability of B given A? Well, the probability of B given A is equal to the probability of B intersection A over the probability of A. And I've given this probability of B intersection A, it's just this. This is equal to the probability of B times the probability of A given B over the probability of A. This is called Bayes' rule. Actually, I should say Bayes' rule is all of this. So putting it into terms of the question that we had before, how do I find the probability of a disease given a symptom? Well, we know that that's equal to P of D intersection the symptom over the probability of the symptom. okay? And we know that the probability of the symptom given the disease is equal to P of S intersection D over P of D. So this tells us that P of D times P of S given D is equal to P of S intersection D, which is also equal to, by symmetry, D intersection S, so that if I come over here, the probability of a disease given the symptom, I just come back over here and I go, well, that's P of D times P of S given D over P of S. And again, this is just a statement. This is just another way of stating Bayes' rule, but in this particular instance, we are stating it in terms of diseases and symptoms. Okay, so let us consider an example here. And I'm going to go back to this slide here. And I'm going to come down a little bit. And I want you to consider this example right over here. Now, notice that what's going on, this is just like I explained to you before about the Center for Disease Control. I've got diseases here, and I've got the probability of these two diseases, and then I've got symptoms, and I've got the probability of these two symptoms, and then what I have down here, these are the conditionals. And notice what these conditionals are. These conditionals here are what are the probabilities of the symptoms given the disease. Okay, and we have these different numbers right here. And now a patient walks into the office and the patient is presenting yellow skin. So remember, the problem that I am presented with here, if I'm the doctor, if you're the doctor, here's a patient coming in with this symptom, yellow skin, and we have to decide which one of these two diseases it could possibly be. So basically what we need to do here, and let me see if my pen is working. Yes, it is. I need to figure out what is the probability of pickled liver given yellow skin. And then I have to also figure out what is the probability of iron poor blood given yellow skin. Okay, remember what's going on here now. Notice what I'm doing here now is I'm trying to figure out the probability of a disease given a symptom. So I'm going to calculate both of these, and whichever one of these gives me the bigger number, I will say that the corresponding disease is the correct diagnosis. So when I come over here, so the probability of a pickled liver given yellow skin is equal to the probability of yellow skin given pickled liver times the probability of pickled liver, and that whole thing is divided by the probability of yellow skin. This is just Bayes' rule that we've done over here. And I've done the same thing with iron poor blood. And what has happened here is, as we can see, now remember these are negative exponents here. This is a much bigger number than this one over here. Okay, so the conclusion is the patient has iron poor blood. Okay, and this is how abduction works. Now we will take this one step further. Okay, so first of all, this is just a statement of what we did before. What we do over here is we just consider, we calculate this quantity over here and we ask what disease maximizes this number. And when we find the number that when we find the disease that maximizes that number, that's when we say that we will consider that disease as the proper one. But now, as this slide indicates, the plot thickens. The patient shows up and has two symptoms. So the patient is showing yellow skin and bloodshot eyes. And now what we have to do is, as things get a little bit more complicated, we want to know what is the probability of this disease given these two symptoms. Okay? And here we have to make some simplifying assumptions here. Um, okay, so first of all, for single diseases with single symptoms, what I want to do here is I want to make some assumptions. Assume that there are M diseases and there are N symptoms. I want to know how much storage is this all going to take up? Well, the probability of the diseases is going to be M numbers, and the probability of the symptoms is going to be N numbers, and then these conditional probabilities is going to be M times N. So that if I look at the total storage here, it's going to be M times N plus M plus N, okay, which we say is on the order of Mn. Now that's with single symptoms. But what happens here, the problem you have when you have multiple symptoms is you don't know if the symptoms are independent or not. Okay? So what we do here to make things simple for us, and this is just a simplifying assumption, and we're not even guaranteeing it works, we are going to assume that the symptoms are independent. But now let's follow some of this through. So first of all, if there are multiple symptoms here, when I want to look at what are the problems of these two symptoms given a disease, that's going to require mn squared storage. Okay? The probability of these two symptoms like that is going to require n squared. Okay? So we can see that all of a sudden now our storage requirements are going up. Okay? So we make what's called the naive assumption. And the naive assumption is that the symptoms are independent among the people at large. Okay? Now, nobody says that this is the correct assumption. And in fact, what you need to do is if you want to make the naive assumption, then you have to make some experiments. You have to do some experiments to see if it gets you good results or not. If it gets you good results, then you go ahead and say, all right, I'm going to make the naive assumption. Otherwise, you've got to throw the whole model out. So what happens here is remember, if the symptoms are independent, then the probability of these two symptoms here is just the product of them. Okay? And we would also have the case that if the symptoms are independent, the probability of any one symptom given a disease and another symptom would just be this conditional probability over here, that this symptom Sj doesn't make any difference at all. Now, when we make that assumption, then what's going to go back here is again, this is our storage requirements right over here, as it was with the single symptom. It's not this case over here. Because what happens over here is now when you want to talk about what is the probability of S1 and S2, you have more storage requirements, and there also may be the fact that the symptoms are not independent. If the symptoms aren't independent, then there are even more numbers to store, because you have to store, what is the interdependence between the numbers. This is sometimes referred to as the covariance, okay, or the correlation between the two numbers. Storage requirements go up. And of course, what's going to happen here is very frequently there are more than two symptoms. So we can see that this number is going to get much, much bigger. So here is the final result right over here. And maybe I should write this out just so that it's a little bit clearer what's going on here. So for example, if I want to know what is the probability of a disease given S1 and S2, according to this, it's going to be the probability of the disease, and then it is going to be, let me see if I have this. Forget this nonsense over here. Let's just look at this up here. It's going to be the probability of S2 given the disease times the probability of S1 given the disease, and that's all going to be divided by the probability of S2 times the probability of S1. And in fact, if I wanted to talk about what is the probability of a disease given S1 and S2 and S3, that is going to be equal to the probability of the disease times the probability, let me rewrite that, the probability of the disease times the probability of S3 given the disease over the probability of S3. I'm just rearranging terms here. Times the probability of S2 given the disease divided by the probability of S2 times the probability of S1 given the disease over the probability of S1. And in fact, you can see that as I add more and more symptoms, I'm just adding more factors that look like this. Okay. Remember, what we've got to do is if we have multiple diseases, we have to figure this quantity out for each one of the diseases. Okay, and whichever disease makes this number the biggest is the disease that we have. The other thing that you should note is notice that the denominator here, and this is all multiplication here, the denominator has nothing to do with the diseases. And in fact, just for purposes of comparing, we don't even need the denominator here. We could just calculate the numerators. The one last thing that I want to say here is these in general will not be probabilities. In other words, if there were two possible diseases, D1 and D2, you could calculate this quantity for D1 and you could calculate this quantity for D2, and the sum of those two quantities would not be 1. Okay. Now, some people are bothered by that, and what you could do is you could normalize them. So that what you could do is you could you could sum up these two things and make that the denominator, and then put in the numerator the sum of you could put the probability of D1 or the probability of D2. If that's not clear, I think I can come over here and do this. Let me do this. So remember, we said the following. Suppose there are two diseases. D1 and D2. So I could come over here and I could say the probability of D2 given S1 and S2 is equal to, and I just go back, first I want to just review what is the formula there. Okay, so it is the probability of D2 times the probability of S1 given D2 times the probability of S2 given D2, and this would be over the P of S1, and this would be over P of S2. And if I came over here and I said, well, what's the probability of D1 given S1 and S2? That would be equal to the probability of D1 times the probability of S1 given D1 over the probability of S1. And that would be multiplied times the probability of S2 given D1 over the probability of S2. Okay, now what we could do is we could say that we come over here and we look at the probability of D2 over S1 and S2, and we put that over the probability of D2 times the probability of S1 and S2, and to that we add the probability of D1 times the probability of S1 and S2. Okay? Actually, I just made a big mistake. Let me erase this. Don't listen to your teacher. He's trying to rush through the end of the lecture here. Let me get this right. Let me get this right. All right, so this is the probability of D2 given S1 and S2 plus the probability of D1 given S1 and S2. That's what I mean by normalize it. So that would be the probability of D2, and then we could talk about the probability of D1 given S1 and S2. And we put that over the probability of D2 given S1 and S2 plus the probability of D1 given S1 and S2. So we could say that this over here, now it's normalized. And remember, what it means by being normalized is it means if I add this plus this, that's going to sum up to 1. So we could say, if we wanted to, we could call this the probability of D1 given S1 and S2, and we could call this the probability of D2 given S1 and S2. So I am going to go back. One of your homework problems is going to be, in this situation right over here, if the patient presents both symptoms, which disease do they have?